Hello everyone. Today the topic of presentation is high-level synthesis introduction. Hello. Is this okay? Okay, and this is the outline. It's first the overview and the lab one and create a high-level synthesis project. And lab two using the TCL command interface. And lab three we will using a solution for design optimization. So the overview, this tutorial introduces the VT's high-level synthesis, and you can learn the primitive text for performing high-level synthesis using both GUI and TCL environment. And this tutorial will also show how to optimize derivative transform and initial RTL implementation into low area and high throughput. And this is the source code of this tutorial. And this source code is FIR filter. Yes, you can see here. So step one, we will explain how to set up the high-level synthesis project and performs all the major steps in high-level synthesis design flow, include the validate the C code and create the synthesis solution, and synthesis the solution, and verify the RTL and package the IP. So the step one is create the new project. It's very simple. And then we will add some design file and add the bench file, and also we have to set the solution configuration. And the step two is validate the C source code. And the test bench will set the output in the output file, and the file name is out.dat. And the output file is compared with the golden results. And if the output is match the golden data, and the test bench main function will be set to 0. And if the output is different from the golden result, and the return value of the main function will be set to 1. And the test bench file here, and the top level C function main, and which is in turn called the function to be this main function, and we will call the function to be synthesis in the test bench file. And the step two, after you run the C synthesis, C simulation, and the console panes will confirm the simulation executes successful here. And this is a tip: if the C simulation ever fail, and you can select the launch debugger option in the C simulation dialog box, and you can use the debugger to fix the problem. And the step three is high-level synthesis. And in this step, we will synthesize the C design into a RTL design and review the synthesis report. And we can see in the perform estimate pane, the clock period is set to 10 nanoseconds. And in this case, VT's target the clock period of clock target minus clock uncertainty. So in this case, it's 10 nanosecond minus 2.7 nanosecond, and it will equal 7.5 nanosecond in this case. So here the estimate clock period in worst case is 5.7 nanosecond. It meets the 7.3 nanosecond timing requirement. And here is the high-level synthesis, and the result utilization we estimate because this is the estimate because RTL synthesis might able to perform additional optimization, and this figure might change after RTL synthesis. And then is the RTL verification. The default option for RTL co-simulation is perform simulation using the VT simulator and Verilog RTL. And this also in the test bench, if you pass the main function will return the value. And here is the IP creation, and the IP package will create a package for Vivado IP. Yes, and we can see here in this file. And lab 2, using the TCL command interface. And so in this lab, we'll exercise how to create a TCL command based on an existing VTIS HL project and using the TCL interface. For the step 1, we have to create the TCL file. And the file script.tcl is contain the TCL command to create a project with the files specified during the project setup. So we need to copy the TCL file from lab 1 to lab 2. And the step 2, we need to edit the TCL's file. So first, we have to add the reset option. And this option is because we typically run TCL file repeatedly on the same project. And it is best to override the existing project information. And the reset option is also have the function is remove the existing solution information when the TCL file is rerun on the same solution. And if the previous project contain any directive you wish to reuse, and you can copy that. And step 3 is run the TCL file, and you can open the VTIS HL command prompt window and type this command, and the VTIS HLS will execute all the steps covered in lab 1. And when finished, and we can see the result is available in this project directory. Yeah. And the lab 3 is using solution for design optimization. And this step will exercise using the design from lab 1. So first, we need to create a new project and optimize the I/O interface. And the first optimization is create the correct I/O protocol and ports. And the type of I/O protocol, you select my affect what design optimization are possible. And in this lab, the I/O requirements are port C must be a single port RAM access, and port X must have an input data very signal, and port Y is the output data very signal. And in here, port C is already a single port RAM access, and port X is by default a simple 32-bit port, and it is an input data port with associated data very signal by specifies the I/O protocol AP value. And the port Y is already associated with very signal, and this is the default option. So to preserve the existing result, we create a solution 2 and apply the optimization directive to design. We can see here. And the step 3 is analyze the result. And in lab 1, we can see the synthesis report. And however, the analysis perspective provide greater detail in interactive manner. So this is the lab 3 analysis perspective. And we can see in the first day, we will read the operation on port X here. And then we look into the loop. The first, the loop iteration count is checked in these 2 commands. And then we read the memory in block RAM in here. And here is if the loop is the final iteration in this loop, and this will work. Yeah. Then we read the port C and do the multiplication. And the final in the final iteration, and the loop will exist, and the value will write to port Y. And the step 4 is optimized for highest throughput. And by default, the loop is kept in row. So in row, and we can reuse the loop for each iteration. And you can also unroll the loop to allow all operators to occur in parallel. And the second is the block range used for shift register. And because the shift register is an array in C source code. However, this prevents it implement as a shift register. So we should partition this block range into individual registers. So step 4 is create a new solution and insert a directive to unroll the loop. Yeah, here. And also partition the array in here. So in step 5, we can compare the report. As we can see, the solution 3 get the small least latency and interval. But in here, but it also get more utilization in here. And I use pipeline to further optimize this design and in the solution 4. And it can further reduce the latency and interval. Yes. So the conclusion. In this tutorial, we will learn how to create a bit-by-bit high-level synthesis project in GUI and TCL environment, and execute the major step in HL design flow, and create a new solution and add optimization directive and compare the result of different solutions. Yeah. And thanks for listening.
One more question, that at the end, the optimization solution 3, that the latency is the question is, how do we know the throughput? That would be the interval, right?
Yeah.
Yeah. So this function, is there any place that shows that, you can come back to the, yeah. One of the solution 3 is, solution 3 that has latency 7. The interval is 8, right?
Yeah.
Interval, that's the interval, right?
Yeah.
And there's the 8, right?
Yeah, this is the interval.
So the throughput means, so every 8 cycle you can fit 1 day.
Yeah.
But remember, within the lab, next week, you can do 1 cycle.
Yeah.
Every cycle. So what's the latency here in the optimization?
Because it has the if condition, it has in source code, you can source code.
So for the optimization is the pipeline. And you enroll it, right?
Yeah. The main difference is over here. Yeah. It's the if else condition we need to check. The next week is up.
So in this loop, you do you still keep the same code. You didn't move out the key. No.
Yeah. In this tutorial.
And so after the solution 3, you didn't. If you have the schedule viewer, then you have to set that here. The conditional statement inside the loop.
Yeah.
What's the effect?
Let's see.
So first, you do the enroll, right?
Yeah.
Okay. Do you separate the shift part and the next part?
In this analysis is the solution 2. This is not solution 3. So
okay.
yeah. Solution 3 is we analyze this result and we do the optimization.
What optimization you put down?
The step 3 is unroll the loop and partition the array. Yeah.
Okay, you partition, what array you partition?
The shift register.
Shift register.
Yes.
Okay. How about the coefficient?
Yeah. In.
C is the input port.
Yeah.
Coefficient is the input port.
Yeah.
And so from C, what do you do with the C?
And in the.
Do you do the repartition from C?
No, because. No. Because in the tutorial, the C port is default is the RAM. Is the RAM type. And
it's a RAM, right?
Yeah. But in VTEX, it default is not a RAM. It just it already be partition.
C is a partition.
Yeah. Its default is already been partition.
Okay, let's do this way. Because in this lab, the final solution to the latency and the interval is now 1.
Yeah.
Like time. So can you, in the discussion forum, tell us what needs to be done further to get the interval?
I think it's remove the if else condition. It can do that.
Okay, so can you experiment? Not here, not.
Okay.
I mean, after the class,
Okay.
you go back to experiment to remove the if else and see what's the interval.
Okay.
And then let us know.
Okay.
Can hold on the discussion on NTU.
Okay.
Yeah, and also, in this lab, there are also some interesting things, which is we talk about using the LUT rate. Let me see, you go back to this is the level 1.
Yeah, that's one.
There's a resource list that you will see the memory. Okay, memory here. Yeah. Okay. So pay attention here that for small array, HLS is not enough. They don't use the dot rate. Because the size, if the size is less than 1 KB, that you will use the LT rate. Okay, so it's quite important to read those reports, especially when you try to get familiar with the tool. So you need to be very careful to study the report. Here, I just want to highlight, when you read it, you will find out, oh, the LUT used for grade. Then what's this for? For what? For it's rare. Do you think that's for coefficient or for which valuable? You think resources?
It might be coefficient.
Maybe
Yeah.
coefficient. Okay, so, yeah.
Okay. Thank you.
Thank you.
And the topic I choose is C validation. And in C validation, I will describe how to do C simulation. And the test bench, which test bench is good. And I will describe the debug mode in the C simulation. And the test bench first, we should create a set of very so that confirm the function is correct. And we also can use a TST to store the golden data. And second, the DUT is called to generate result. And third, the actual and the expected result are compared. Then we can know if the code has any problem. And this is the test bench. And first we can see the for loop, and the for loop will calculate the expected value. And then we will call the actual value.
Oh, okay, okay. So,
And first we can see in the for loop, we will calculate the expected value. And first, we will calculate the test data and the coefficients, and then we will multiply to the SW result. And then we will call the DUT, and this is the actual result. And then we will compare the two data in the if else. And if the data is not the same, and the error counter will plus. And in the end, we will use the if else to find if the code is correct. And if the error count is not 0, then it will print test fail. And if the error count is 0, then it print test pass. And in C validation, first we will add the C code and the test bench into the project. And we will run the simulation by clicking the button, and then it will display the block. And first we can not choose any mode, just run the C simulation. And then we can see if the test is passed. And then we can choose the launch debugger to do C simulation in the debug mode. And this is the debug mode. And first we can see in this, and in this we can change the mode to debug or to synthesis. And we can use the button to run the code. And then in this pointer we can see the index which the code is running. And in the table we can see the variable in this code. And in this lab, it will do 3 labs. And the 3 labs is the same design, but in a different position. And in the tutorial, the situation of debug will change due to the different precision. But in version 2020.2, the debug environment can run in the 3 different positions. And in lab 1, the data type is standard C type. And in lab 2, the data type is arbitrary precision type, and it is provided by VT's high-level synthesis. And in lab 3, the data type is also the arbitrary precision type, but it is provided by C++. And I use the lab 3 for example. And this is the screen after I launch debugger. And we can see when we launch debugger, and we will change to the test bench. And then we will change to the Hamming window.cpp. And this is the design code. And we can set the breakpoint. And we can set the breakpoint by double click the row, and we can set the breakpoint. And then we can check our breakpoint in this. We can change to the breakpoint and see where is the breakpoint we set. And then we will click the return in this. And then it will create the submodule. And we can check the submodule we define in the row. And then the pointer will change to the breakpoint we set. It's the for loop. And then we will click the step into button. Then the pointer will change to row 63. And it means that if we click the step into, then the code will run to the next line. And we can change to the variable to see the data in the for loop. And when we click the step into again, then it will change to the API-NT.h. And this is the this is the file we called the precision, and this means that the next step will jump to this code to do some computation. And we will click the step return to the timing window.cpp to run our code. And then if we click the saving tool again, it will jump to the AAHLS-NTU-2021Fall. And this means that we also calculate the data in this precision. And we also click the saving tool again. And then when we click saving tool, then it will jump to the AAHLS-NTU-base.h and jump to this file. We will do multiplication, and we can see the pointer is in this line, and this line is to do the multiplication. And when we click the step return again, then we can find that the pointer will change to the row 61, and it is the first line in the for loop. And when we click the stepping tool, then we can find that the I will change to 1, and this means that the for loop will run for a second time. And when we click step into or step return, then you will display like when the I is 0. And conclusion is the debug environment is a good way to find out what's wrong in the code, because we can do the C code step by step. And we can find the data flow is go to which file. Yes. Thanks for listening.
So in the simulation, first you will run the C simulation.
Yeah.
Okay. And then in the C simulation, the kernel function still using the arbitrary procedure.
Yeah.
Okay. So and then you also have the data calculated using the host test program using the C code, which run the local processor.
Yeah.
Okay, and that local processor is going to use the local floating point operation.
Yeah.
Okay. And then you will check against your kernel power to compute its result.
Yeah.
So there are two things. One thing is when run the C simulation, the arbitrary precision library will be exactly same as the hardware computation. Right?
Yeah.
When you run the C simulation, actually the kernel function using the silence arbitrary precision library.
Yeah.
And then you synthesize the hardware. Okay. And then the hardware will be exactly similar to the software.
Yeah.
In terms of precision.
Yeah.
And then the hardware, then the second level is you have a C source code, which has bench. You calculate the expected value.
Yeah.
And the expected value is using the local processor.
Yeah.
Right? They're using the floating point processor, the local processor.
Yes.
these two, they have a variation. Right? Especially for floating point.
Right.
Because in the local processor, the floating point is implemented following the IEEE standard, and the kernel function, the high-level synthesis, may not be exactly the same as the IEEE.
Yes.
So there is an error to be introduced. So for when we run the C simulation and the costing, especially the costing, that we want to find the difference. And the difference sometimes is important, especially for scientific calculation. And also for certain, sometimes you need to accumulate, and there's a rounding issue. So C simulation also you use to compare the error accumulated and whether it can be accepted. So that's why in this lab we take the arbitrary procedure.
Yeah. Okay.
I didn't find mine.
Or if it's not updated, go to another folder.
Oh, okay.
Go to this one.
Okay.
Yeah.
Thank you.
Okay. Hello? It's so slow. The file may be too big.
Yes.
It's a big file, right?
Yeah.
Oh, okay.
Okay.
Yeah. And then click start.
So if I want to change the page, I just
You can select. Yeah.
line or touch the
Touch
screen.
is okay. Yeah.
Oh, okay.
Touch is okay. Yeah.
Okay, thank you.
Just the tab.
Hi, this is the oral presentation of Lab A, and the topic I want to share today is interface synthesis. And this is the outline today, and each section maps to one lab, roughly one lab here. And okay, that's the overview of the interface synthesis. It plays an important role to let C design communicate with outside by adding physical RTL ports to the C design. And in addition to this, it also includes an associated I/O protocol, which allows the data transfer through the port to be synchronized automatically. And this is the source code in this lab. In lab 1 and lab 2, just implement a single adder because in these two labs, we just compare the different protocol. Oh. And these two labs has a different way to pass the output data. In lab 1, we pass the output data by function return. And in lab 2, it pass the output data by pointer argument. And this is the source code of lab 3 and lab 4. We do array partition and optimize it. Okay, first I will introduce the block level protocol, which is mapped to lab 1 here. There are 4 options for block level protocol. And in this lab, we compare the difference between AP control none and AP control handshake. And I won't talk about AP control chain because it is not mentioned in this lab. And AXI lights will be discussed in lab 4. Okay, this is the result using AP control none. We can see there's no control signal in the interface. And because AP control none means use not use any protocol. And if we use AP control none, there might cause some problem when running code simulation in VTHLS. Yes, okay. And this is the.
So you say that AP control none now run the posting.
Code. Oh yes. Just like the lab 1 in this class, we have to remove that pragma to run code simulation.
Posting kind of tend to have a single protocol to send some data from the Rtl.
Okay. So let's continue. This is the signal behavior. So in AP control handshake. And I think the name is very straightforward. For example, AP start means the design start operation. And AP ready means that the design is ready for new input. Okay, and then this is the result of AP control handshake. And on the right hand, this is the waveform of the signal. And this is the options for port level protocol. And there are many of these. There are 9 of them. And we just introduced 3 of them, AP acknowledge, AP valid, and AP handshake in this lab. And AP technology means with the data port, there's another associated port to let outside tell the design that the data has read or written. And AP valid is that the data port is with another valid port to tell outside that that data is ready for reading or writing. So I think AP acknowledge is transfer the data in a more passive way, and AP valid transfer the data in a more active way. Oh, okay. And AP handshake has 2 associated ports. Valid and acknowledge port, and it provides a 2-way handshake communication. Yes, okay. This table shows the relationship between function arguments and post protocol. And the block in gray means that that kind of protocol is supported to this type of function argument. And each function argument has its own default protocol. 对。Okay, this table is copied from the AAHLS textbook. And this is the source code of Lab 2. As I mentioned before, the argument is passed by the output is passed by pointer argument, and it provides a bidirectional port if it is both input and output. And after synthesis, these arguments will be separated into input and output ports, and so are their associated ports. And this is the result of Lab 2. And as I said, that the in-out one port will be separated into input and output ports. Okay, and this is the Xi4 interface. There are 3 types of Xi interfaces. First is Xi4, and it is for high performance memory mapped requirements. And the next one is Xi4 Lite, and it is for simple and low throughput memory mapped communication. And the last one is Xi4 Stream. And this one is for high-speed stream data. And it doesn't transfer the address information in this interface. Okay. 我从这一页开始讲中文好了，因为就是这一页是我有比较有问题的地方。好，就是我对这个东西的理解，因为我觉得这3个东西有点让我 confused， 就是我不太理解这3个东西的关系。然后，所以我的理解是，block level protocol 是传输最上层那个 top function 的资讯嘛，就是让这2个沟通的。
就是说，我不会讲。Block level 是这个 module level， 就说我这个 module 要不要去调它，然后 core level 是这个 module 的 I/O。
哦。
So first you need to start imagine that when you do the design, there's a module design. So in the module that let's say you have a state machine control the whole module. So that state machine needs to have a trigger to start. Okay. So we're waiting for the AP start to kick off the state machine. And that state machine, the next state will be read the input. Then the core level protocol comes into play. So you can take a block level protocol is the state machine of the whole module. And for each trigger, it goes to the next state. That state is the IM state. So for the second state, then it will be the core level protocol.
Okay.
And you say big things, block protocol.
Oh, Xi interface.
On Xi interface, okay, Xi interface, many as a kernel function need to communicate with host. Okay, let's say I design a module, and the module you may have a multiple module interface into a bigger module. Okay, in that case, you don't use the Xi interface. That's too complicated. So you use a simple protocol like the AAHLS, okay, or internal stream. And then when it comes to the kernel function, and kernel function interface with host. Okay, there are two types of the host interface. If you look at the PCIe, could be a PCIe, or in the NTSoC, that's the TSP interface. TSP interface that has only Xi interface, right? Okay, so you need to package. Okay, let's go back. Let's solve since people don't understand. Let's go back to this one. Let me go back to my PPT. There will be interface. Let's see. You need to come back to. Let me see. Come back this one. Okay. Confirm. Let's explain this one. Okay.
Okay.
Yeah. So when you do the HLS, VT's HLS synthesis that create an IP level. Okay, remember you have an IP level, kernel level, the target, different target. 是没有其他的可能性的。
有。
Okay, so those interface here. Look at here. AP star, AP down, and those if it's a FIFO interface, those empty read, right? And AP bus, those interface. Okay, those interface is the IP level interface. So you create a module that you use a simple interface, and then to connect these two modules. Okay, then you use this IP level interface protocol. Okay. However, when you want to talk to the host, okay, for example, in the NPSoC, there will be a Xi interface between PS and PL. Or if it's PCIe, you interface with the PCIe IP, and then PCIe goes on the I/O bus. But the PCIe IP, when you interface with the PCIe IP, that it uses Xi interface too. Okay, so when you do the IP integrator, then it generates those adapters, and then becomes those Xi interface. Right. Yeah. And then you use a block design to hook on some infrastructure component like DMA or fabric interconnect. Yeah, and then it goes on to the PS side interface. Yeah. You understand? Yeah. And yeah. And one thing I particularly want to mention is the stream interface. Stream. Okay, don't be confused. The HLS, they provide HLS column stream. That's the a template function that implement the stream. And we use the stream a lot for the module interface between modules. Okay, that stream is different from the XI stream. Okay, XI stream is when it becomes a kernel function, they follow to the XI protocol. That's the XI stream. Yeah, and the internal stream just a very simple FIFO interface. Yeah. Okay. Yeah. So we use a simple protocol for the module interface. When you interface with the host, communicate with the host, you have to use the XI interface. That's how you talk to the PS side of the PCIe host. Okay, yeah. So let's go back. I don't know if you, yeah. But it's good that you raise it.
To tell the truth, I'm confused too in the early days. Not just you. Okay. So your will be here. But no. Oh. Oh. Okay. Yeah. No, not this. No, not this one. Oh. This should be here. No, not this one. It should be here. And then here. Okay, so yeah. Yeah.
Okay, so thanks teacher a lot, and I will go to the next page. And this is the default protocol in Xi4, which is also copied from the HL textbook. And we can see that Xi is a very important interface here because it's used in many situations. And this one is the result when the port protocol using Xi4 string. And on the right-hand side, this is the associated port of AXI string. Okay. Oh. Okay. And this one is the block level protocol using AXI Lite. And the right-hand side is the associated port of AXI Lite. And wait a minute. If we use AXI Lite, the HLS will generate an associated set of C driver files during export RTL process. Okay. And this session is talking about array partition and its optimization. Oh, really? Sure. Okay, and in lab 3, we used array as our argument in this function. And there are two partition types when we partition the array. There's block and cyclic. And if we partition the array in 8 blocks, then the index 0 to index 3 will in the first block, and the index 4 to index 7 will in the second block. And if we partition the cyclic in a cyclic way, and then the assume that the size of the array is 32, and we partition in 8 cyclic block, and then the 0, 8, 16, and 24 will in the first block, and the index 1, 9, 17, and 25 were in the second block. Okay, and this is the algorithm.
If you operate the data sequentially, okay, and if you want to do the parallel operation, then you use it.
Oh.
If you put the consecutive elements in different blocks.
Oh,
In that case, you can get their access.
okay. Okay. This is the algorithm in the source code, and this is the input array, and this is the output array. So the output value will be the sum of the input value in the same column. And then in this lab, we partition the array in 4 ways. First is no partition, and the second one is partition the input array into 2 blocks. Okay, and then the third one is partition input and output array into 4 blocks, and the last one is to fully partition the array. Okay, and because those 4 methods are not the optimized one. So we can see that in this array and in these 2 arrays, each column is independent with each other, and so the best way to partition the array is to cut in 8 cyclic blocks. Okay, and so also because that each column is independent, so we can unroll the loop as well. And we also do pipeline on it. And this is the results to compare different partition way. We can see that if with no partition, that the latency will be the maxima, and the hardware resource will use the less hardware resource. And if we cut the array fully, then the latency will be the minimal one. And the optimized one is acyclic and unroll the loop. Then we got the minimal estimated cycle time here. Okay.
Say 2 blocks, that means fully enrolled.
Huh?
Yeah, 32 blocks.
The partition way above the 32 blocks are all rolled. Only these 2 has to loop unrolled.
Oh,
okay.
So the latency was that's a one iteration. That's the iteration latency. What was the latency?
This latency is the latency on the summary of the synthesis report. There's max latency and minima latency on the table.
So that's the whole function. The loop latency. So the dual cyclic control. Latency control. We need to show the detail
of the information. Oh, okay. Okay. Okay, and this is all the presentation today. Thank you very much.
So that's one question. That's the IO port, right? The IO that you using the array partition, not sequence. So the problem for you do the whole thing. The lab doesn't do the whole thing.
No.
When you do the whole thing, there will be trouble, and especially in the lab, the both lab also using the stream interface, right?
Yes.
So you do the cycling. You do the okay. That's an IO code. Let's go back to this.
My question is, maybe is one slide. Okay, so you have a module pool, and you have an array, right? Okay, and this array, you want to do the array partition. Okay, and you use a cyclic. Okay, so that means the data comes in like 0, 1, 2, 3, and then 8, 9, 10. Okay, for each array. Okay, cyclic. And also, further in this lab, you make this another array. You make the string, right? Each one becomes a string interface. Yeah. So my question is, when you do the co-simulation, so this that's the host program, and internal there is a wrapper. When you do the co-simulation, the host, I believe in the host you also declare this array and you prepare the test data, go into the I try to put things together, yeah, because this lab didn't talk about these things, yeah, and then it stopped, yeah, it doesn't do the code simulation. Let's try to imagine you do the also the optimization on the module IO cores, okay, and then you want to do the code simulation. So what thing involved in this process? Okay. Especially you do the cyclic, you partition, array partition, and further you make it a string. And then you want to simulate this stuff. Yeah. And then in the host side, the host program, when you prepare the test data, you simply put the test data into this A array. Yeah. And this one is run in Verilog simulator. It's run in the simulator. And the simulator need to feed it runs cycle by cycle and need to feed the data in. Okay, and the host program is A array. Yeah. So you got to have something here, a wrapper. Yeah. To prepare all the data to test this module.
Oh.
Right?
Yes.
Yeah. So this wrapper will do something like maybe it becomes a 8 array, and try to fit this partition in here, and then it has a interface module. Okay, each time fit one A data, each cycle to emulate the string interface. Yeah. Okay. Okay. Yeah. So just give you the whole picture of how this is proceeding. Okay. But for detail, you can read the test bench source code, the code. When you do the, I think the code sim. When you run the code sim, you look at the directory, you will find out the wrapper, the module wrapper. then you can go study it, yeah, see how the host program interacts with the design for doing the hardware simulation. Yeah.这500元，
对，应该还好。
还好。
请问这个是没有更新的吗？
这个是更新的，这应该是更新的，赶紧看一看。哎，我刚才是在哪里掉下来的？这个吗？好像不是哦，不是哦，哦，这个没有更新的，好，先走掉，不能跟走。好，大腿，没错。可以扔掉。单机啊，就那个PowerPoint的话，那等一下。哦，PowerPoint把它弄掉。哦，把这个关掉。
那个往上滑掉。
就是再重开一次。哦。哎，还在漏。如果可以上滑，下滑。哦，没有，就是要先按2下，然后就可以把它往上滑掉，上滑掉就没了。照理说应该是就关掉了。哎，好，所以我应该是这个。对吗？好。OK。
开始。Okay, so hello everyone. My topic is arbitrary precision data type. So this is the outline. I will first give a brief introduction about this tutorial, and then give some background about the fixed point numbers and floating point numbers. And then I will introduce the design, the kernel design and the host code. And then it's about the trade-off we can make using the arbitrary precision data type. And finally conclude this tutorial. This is about the introduction. So in this tutorial, we are using arbitrary precision data type. So basically, we would like to use fixed point numbers instead of floating point numbers to perform the computation in our design. and the computation for fixed point numbers is cheaper, and we can decide how many bits we use to compute the number. So we can use just the amount of bits we needed. So in this lab, we will show how to use arbitrary Bayesian data type in our design and compare the computational precision and the performance and power usage between using floating point numbers and fixed point numbers. I will first give some background about floating point numbers. So a floating point number is a bit stream, and there are three parts. The first part is a sign bit. So if the sign bit is 0, then the number is positive, otherwise it's negative. The second part is the exponent. And the third part is the fraction. So the exponent part, the number here, we have to minus 127 to get the real exponent you want to represent. So in this example here, the exponent is -3. And the fraction part, to interpret the fraction part, we have to add 1 point in the front of the fraction. So in this case, it is 0, 1, and we have to add 1 point in front of it. So in this example, the floating point number here is 1.25 times 2 to the -3. And when we add in two floating point numbers, we have to first shift the numbers so that the exponents are the same, and then we add the fraction part. And finally, we may need to normalize it back. And for multiplication, the exponent part are added and the fractional part are multiplied. Next is about the fixed point numbers. So here shows an example. It composes of the integer part and fraction part and a radix point. And to interpret the number, so the integer part we just interpret as a binary integer, and the bit after the rest point, the first bit after the radix point is 2 to the -1, and the second is 2 to the -2, and so on. So the number here is 2 to the 3 plus 2 to the 0 plus 2 to the -2. And as we can see, there will be error for both fixed point numbers and floating point numbers. So for example, if we consider the floating point number 1.8, if we use 3 integer parts and 2 fractional parts to represent it, the closest number we can represent is 1.75. There will be a error 0.05. And if we increase the fraction part to 2 bits, then the error can be smaller. But in fact, to represent it, we need infinitely long bits to represent it in binary. And for addition and multiplication, we just need to treat it as integers with special care about the radix point. So we can see that the computation for fixed point is cheaper than that for floating point. But the expressed power for fixed point is weaker, since the fixed point can only be at a particular position. Okay, so next I will show the kernel design for this tutorial. So first, we will compute some coefficient. So in the example later, we compute the coefficient of a hand window. And then for each input, it is multiplied with its corresponding coefficient and become the output. So this is the kernel design. And in the design, the data type to perform the computation is defined by these 3 types. So for the floating point design, we use the float in the C++. And if we want to use arbitrary precision data type in the design, we have to first include these header files. And then we define this data type using APFix. So for APFix, WIW, it means fixed point numbers with totally W bits, and the integer part has IW bits. So in this case, so the 14 point is 32 bits, and in the fixed point design, they are set to 8 bits, 24 bits, and 18 bits. And then it's about the host code. So the host code mainly computes the same computation for software and hardware results. So for software results, it computes the coefficient first and times the input. And for hardware, it is similar. So the coefficient is multiplied with the input data. So it is in fact shown here. There are similar computation, but for the software, they are computed using float. So with the arbitrary precision data type, we can trade off between the computational precision and the hardware usage and timing. So since there will be some error when using the fixed point, so the precision will be low. So first we see the simulation result for floating point design and fixed point design. So for the floating point design, we can see that basically the hardware and the software have the same outcome. Basically, there may be some difference, as mentioned in the second presentation, but here they are so small, so it's not shown here. On the other hand, for the fixed point design, since there will be some error between using floating point and fixed point, but as can be seen, the difference will be smaller than 0.001. Next is about the hardware usage. So the table shows the overall hardware usage for the floating point design and fixed point design. You can see that floating point design need more hardware. Okay, so the floating point design needs more hardware. And particularly, we can see to perform the floating point multiplication, it needs an instance FMUL, which needs 3 DSP and 78 lookup tables. On the other hand, for the fixed point multiplication, it only needs 1 DSP. Besides, since the total amount of memory needed for the floating point design is more than that for the fixed point design, so the tool will need a VRAM for the floating point design, but you only need FreeFAR for the fixed point design. And for the timing, for floating point design, the estimated clock period will be longer than that for the fixed point, and the latency will be slightly longer. So using a fixed point design can achieve a better performance. So to conclude this tutorial, by using the arbitrary precision data type, we can trade off between hardware usage, latency, timing, and computational precision. Besides, using the APFix data type in VTIS, the tool can automatically convert the computation from floating point 1 into fixed point 1. So it is very convenient for designer to decide how many bits needed for the design by running a C simulation. So this is the end of my presentation. Thank you.
Just one thing to mention, settings does provide floating point arithmetic type. That means that's a logic for. So we will perform the floating point result and follow the actual the actual. So if we really want to do very precise result using the theorem, you will get that is the result as the result. But simply too close. So when you do the floating point design, you want to convert to fixed point. That's a very important design decision. How many precision it is. Then you need to do, especially you don't maybe like okay. Oh, yeah. So I just like to say something that of course, they use fixed points that give you less area and higher throughput because cycle reduce. And so when you compare the arrow, that not just when you calculate and then you compare with the floating point and fixed point, the difference between them. So particularly, you need to pay attention to accumulated error. Yeah, because when you do the calculation, that's a iteration on many data accumulated. So the error will be accumulated. Yeah. And also, when you use a fixed point, you have a saturation rounding or different rounding mode. Yeah. How do you choose the rounding mode? And when it's calculate that the error accumulated, whether there's a strategy that when you do the rounding and those things, and then it's a very sophisticated process, yeah, to use the fixed point and then to get the right answer, especially for iterative computation. Yeah, I just like to mention this. That's a very important part of the design process. Yeah. Okay. Okay. So next one. Good. Yeah. So here. Oh. Okay. Yeah. Yeah. Okay.
Okay. So good morning, everyone. My name is my name is Lin, and today I'm going to talk about design analysis. Okay, so here's a review. Why doesn't it move? Oh, crap. Oh, okay. So let's take a brief review of our source code. And this is the main function of our source code. And we can see it has the internal buffer, which is buffer to the in and buffer to the out, which stores the input data and output data. And also we have the three subfunctions, which is read data and DCT2D and write data. And we're going to take a look on both of these three functions. Okay, so here's the read data. And actually it's really simple because the read data, we just transform the input data from the one dimension to the two dimensions. And we can see that, so the buffer is our internal buffer. So we just take the input data and store it in our internal buffer. It then takes two levels of the loops to complete this test. Okay, so this is our main function, which is the DCT2D. Oh, basically this function just practice the DCT2D, and first of all, this is the first loop, which is the row DCT loop. You can see it's right up here, and yeah, great. There's a circle on the screen. Okay, so it irregularly calls the function DCT1D, and you can see here is the brief introduction of the DCT1D. DCT1D contains two levels of the loop. So there is three levels of the loop in this entire function here, entire loop here, right up here. And just for information, DCT size is the 8. And when we are analyzing the latency and the internal level, we'll constantly use this the number 8. And also, you can see here, column DCT loop and the row DCT loop is a symmetric one because they perform the same function. They iteratively calls the DCT1D for 8 times. So the bottleneck are these two functions, and their complexity is the same. The complexity is 8 because the outer loop here is 8, and the inner loop here and here is also 8, so which is 8 times 8 times 8, which is 512. Also, in the middle, the function just transforms the input data from the row to column and column to row, so that we can reuse this internal buffer in the function right over here. We can call DCT1D here without calling another function. And finally, after complete the column and the row of the DCT2D, then we just write it out, and which is lead to another function is write data. And because after we complete the DCT2D, we store it into the internal buffer, which is buffer out 2D, and the output is 1D, so we just use another function, which is write data right over here, and we just transform from the 2D internal buffer to 1D output. Okay, so that's the entire introduction of the source code, and let's this is a brief recap. So each loop size is 8, and as we see that the maximum level of loop size is 3, which is row DCT2D and column DCT2D. And the bottleneck of this operation, the entire DCT2D, is the 512 because we can see that the maximal level of the loop is 3. So which is the 8 to the power of 3, which is 512. Oh. Okay, so here's our first design. The tutorial, this is the first design that is introduced by the tutorial. It says that the design without a directive is the design without a pipeline. But after the experiment, I found that it's not true. Because as you can see the log right up here, it pipeline automatically. The Vitis HLS compiler is very smart. So if you don't put the directive, then it will pipeline for you. Okay, so let's take a look on how this design works. And this is the design without the directive, and this is the schedule viewer. So you can see here there are this one and this one, there are aligned on all functions, which means it is pipelined. Also, this one originally it is a 3-level nested loop, but now it's flattened. So you can see there's only one level of loop right over their design viewer. Oh, sorry, the schedule viewer.
So you say they are flat.
Yeah, these loop. Yeah, default it will flatten. No, no, there is any pragma right over here. Well, the design compiler do everything for you, which is very smart. Okay, so here's the throughput, and you can see the result right over here. It shows that it is flattened because row DCT loop, DCT outer loop is in the same it is shown in the same row, so it proves that it's flattened. And okay, so the throughput is 64 over 68 because you can see the trip count right over here is 64, and the total latency right over here is 68. So we can derive that it completes the 64 operation within the 68 cycles. So the throughput is 64 over 68. Also, we can see the loop is pipelined and flattened, as I mentioned before. Okay, so here's the design, the true design without a pipeline. So to avoid the Vitis HLS compiler to pipeline my design automatically, so I need to put all the directed HLS pipeline off and all loop, so the HLS wouldn't touch my design. So here's the schedule viewer, and you can see there's no line as the previous schedule viewer shown before, and there's no line right over here or here, and you can see all the loop is separate. Here they are both separate and they don't overlap, which means there is no pipeline route up here. Okay, so we can first calculate the throughput of this design, and because the bottleneck is the real Dct loop, so we just analyze this loop, and because the method to analyze the throughput is similar, so I just analyze this nested loop, 3-level nested loop. And for the inner loop, you can see for each iteration, the latency is 5, and the trip count is 8, so 5 times 8 is 40, which is right over here. And to complete one iteration in the outer loop right over here, which is 42, because you need to enter the loop, enter the inner loop, and exit the outer loop, so which takes one cycle individually. So we need to have 2 cycles, extra 2 cycles. So 42 and 42 times 8, which is 336. And after 336 cycle, we complete the Dct outer loop, and then we look into the row Dct loop. And you can see here is 338 because similarly, we need 1 cycle to enter the loop and 1 cycle to exit the loop. So which is 38, I'm sorry, right over here, and we times 8, you can derive that 8 times 338, which is 2074. Okay, so the entire operation is 512 because which is 8 to the power of 3 is 512, and we complete these 512 operation within 2,704 cycles. So the entire throughput is 512 over 270 and 704. Also, you can see if this number of the operation approach to the infinitive, which means that we close the number of the entire nested loop is infinitive, then it will approach to 1 over 5. The 5 is here, the operation of a single, the cycle requires by a single operation. Okay.
So the problem for my loop is not that.
Because I add the pipeline of director for every loop, so they are not flattened. I told the Vitis compiler to don't touch my design. Okay. And here's the pipeline, the inner loop. Oh, so to further reduce our latency, so we need the pipeline. So we add the pipeline in each inner loop. And this is the sensible options because we add the pipeline in the inner loop, so it wouldn't bring about a large area. And also, we can improve the pipeline for the inner loop. Okay, so here's the throughput. And you can see here is the analysis here. And it is flattened. So, oh, I'm sorry, it is pipeline. The inner loop is pipeline. So, although each operation requires 5 cycles, but it only requires 11 cycles in total. But actually, I have a question right up here because for in my calculation, it should be the trip count is 8, and the iteration, the latency for each iteration is 5. So my calculation should be 5 plus 8 plus 5 minus 1 is 12. So I suppose that it should be 12, but the report says that it's 11, which contradicts to my prediction. So here's my question. And also the iteration latency here is 14. And I can understand it because, as I said, my prediction should be 12 cycles right away, and it takes 1 cycle to enter the cycle and takes another cycle to exit the cycle. So it should be 1 plus 12 plus 1 is 14, which makes sense right up here, but I don't know why the report says it's 11 right up here. Maybe Professor Lai can tell me why is that now, or you want after this presentation. Okay. Okay, so now you can see the outer loop is not pipeline, so the trip count is 14, and the iteration latency is 14. The trip count is 64. So you times them together, and it will be 860, 896. Sorry. Okay, so the throughput of the outer loop is 14 over 1, and the throughput of the inner loop is 8 over 11. Okay, so for the inner loop, the latency is 5, but because it is pipeline, so the II is 1, because it can take the new set of the input every cycle. Okay, so here's the comparison of the report. So this report can compare the current design with the previous design here. So you can see that the latency is the total latency is 2058, and the previous design requires 5990, which is a great improvement right up here. However, you can see the utilization. It requires more lookup table and register compared to a previous design. So the pipeline, we need to pay the utilization in trade of the latency. Okay, and so to further optimize our design, we need to look into where the bottleneck is. So we can see right over here, and it is very strange because we pipeline the inner loop, so the inner loop should be flattened and be combined with the outer loop. But instead, the inner loop is not combined with the outer loop over here. So we look into the reason why does that happen. And so you can see there's an operation which is span over the inner loop. And I look into this where this operation is, and in the source code it corresponds to this operation. And because it is not a perfect loop, it is an imperfect loop. So that's why the design compiler, that's why the AAHLS compiler cannot flatten this inner loop with the outer loop right over here. Okay. So we modified the code as Professor Lai taught us. We can move the source code right over here, like into the inner loop, like this one. So there won't be any statement between the loop body. Now we synthesize this new design and we look into the data viewer. We can say that's pretty nice because the entire nested loop is flattened into one loop right over here. And we look into the throughput. Oh, actually, the area I should highlight is just right in the this column and ignore these two ones because it's not in the same loop. Okay, so the latency is 515 and the trip count is 512. So it means that 512 is the entire operation. So the entire operation is carried out in the same loop, and the pipeline is yes, so it means that it is pipeline and it is flattened. So the throughput is 512 over 515. And you can see the latency is 5, but it's okay because it is flattened and pipeline, so the II is 1, because we can take the new set of the input every cycle. But actually, I have a question right over here, because in, the entire latency I calculate should be 5 plus 512 minus 1, which is 516, but I don't know why it is 515 right over here. So maybe Professor Lai can address this problem. Yeah. Why is not 516, but it's 515? Because if the I is 1 and the latency is 5, and then it should be 5 plus the entire triple count, which is 512 minus 1. 516.
So they are all constant.
Yeah.
The loop will be one count.
Yeah. The trip count will be 5 count. Yeah.
So we 1 plus 4 or twice the reduced one.
Yeah. Yeah, it's 1 lower. Yeah. Yeah, that's my question. Okay. So maybe I can move on.
Yeah.
Okay. Okay, so here's a comparison with the previous design. You can see the previous design takes 2059 cycles to complete all the tasks, but now it only takes 1615 cycles to complete. However, you can see the utilization here. We need more complicated logic, so we need more lookup table. And also, we flatten the loop and we pipeline the more loop includes the Dct in the loop, so we need more registers right up here. So here's the trade-off. We sacrifice more utilization in trade-off the shorter latency. Okay, so the modified code is my design, and it is not mentioned in the tutorial. Actually, solution to the previous problem in the tutorial is we pipeline the outer loop, which is very brutal because it will enroll the inner loop. Okay, so we see the comparison reports right up here, and the previous latency is 2058, and the latency now is 586. So the latency reduced dramatically, but because we brutally enroll the inner loop, so it is executed in parallel. So the lookup table right over here, okay, it is increased and we need more registers. So we also use the utilization to in trade off the latency. And now we analyze the throughput here. And because we enroll, so now the trip count here is 8 and it requires 160 latency to complete all the operations. So the throughput is 512 over 116, and because it is more than 1, so we can know that the loop is definitely enrolled. Okay, so to further optimize our design, we need to look into the bottleneck. And the bottleneck right over here, we can see DCT1D takes the largest cycles latency. And so we further look into DCT1D, which is right over here, and we see we can see here it takes 4 cycles to load the data because you can see it corresponds to read. So it means we are loading the data from the SRAM. And because we need multiple cycles to load the data, so we can see that our bottleneck is the memory bandwidth. So to solve this problem, we use the memory partition. Okay, so here's the directive of memory partition. We add the memory partition right over here and right over here, which is the SRAM. Okay, so this is the data schedule viewer of the new design. We apply the memory partition, so you can see here we access the memory in multiple memories in the same cycle. And in the previous design, we only have 1 memory block, but here we have 8 memory blocks. And as you remember, the DCT size is 8, so that's why we need to access the memory 8 times to load the data. And here's the data fetching, and you can see right up here, we only need 1 cycle to complete all the data fetch. Yeah. Okay, and here's the throughput. And here, actually, the only difference is 7. As you remember, the latency here in the previous design is 20, but it is reduced to 17 because you can see we need 4 cycles in the previous design to load all the data, but now we only need 1 cycle. So we save 3 cycles right over here. So that's why the cycles for the inner loop decreased from 20 to 17. Okay, so we save the cycle for each loop for the iteration of 1 loop. And the throughput further increased to 512 over 136. And here's the comparison of a report, and the latency here is 568, but now because we can save 3 cycles in each inner loop operation, so you can have a shorter latency. However, because we partition the memory, so in the previous design, we used a big memory block to store all the memory, but now we use 8 small memory blocks to store the data in the memory. So usually for the SRAM, the bigger block is more compact, and the smaller block needs more area to save the same amount of data. So the lookup table and the flip-flop also increased. So we use more utilization to reduce our latency. Okay, so now because our latency is only 10%, the absolute latency is only 10%, 10% compared to the design without any pipeline. So now we turn to the optimization of the interval. And we want to optimize our interval. And one way to achieve that is using the directive of the data flow. So here we use the data flow directive. Yes. Yeah, because it. Yes. Yes. Interval means that the periods that it takes to accept the new set of the data.
So that's like a birth rate.
Yeah. Okay, so yeah. Yes.
And further optimize for the birth rate.
Yeah. Because we may use the data to the list function, call this function for many times, and if we can improve the interval, then we can start the new set of the input data even when this function is still on the run. Yeah. Okay, so here's the So here's a comparison of reports. You can see here the interval. It was 539, but now it is reduced to 407. So it means that in previous design, this entire function takes 539 cycles to accept the new set of input data, but now it only requires 417. And the previous design, it is as long as the new latency, which means that this function has to wait until all the kernel completes the text so that this kernel can accept the new data. But now we can see the interval is shorter than the latency now, so it means that this kernel can accept the new set of data even when this kernel is still running. Okay, so now we look into the bottleneck of our design. We see where the interval is the largest. And we can see here, data 2D. We look into the module hierarchy, and here the data 2D has the largest interval. And we can see this data 2D is not optimized because we only optimize the top level of the data flow of the top level, but because data 2D is the subfunction, it is called the function called by the top level, so it is not optimized because it is not in the same hierarchy of the top level. So to further optimize data 2D, we can pipeline data 2D. However, it will enroll all the function, and which will bring about a large area because you can see there are many loops in the Dct2D, and the maximal loop is the 3 level. So if you pipeline all the function, it will bring about a tremendous area. So instead, we use inline to optimize the Dct2D. We use inline to bring Dct2D to the same hierarchy to the top level. So when we optimize the data flow in the top level, we can also optimize Dct2D meanwhile. Okay, so here's the module hierarchy here. And we can see here there's no Dct2D anymore, which means Dct2D is in the same level as Dct. Instead, you can see here, these are the loop inside the Dct2D. And they are in the same level with other functions, subfunctions right over here. So it proves that Dct2D is indeed brought into the top level. And here's the comparison report. And because the Dct2D now is in the top level, so its data flow is also optimized. So the interval in the previous design is 407, but now it's only 138. So it means that this kernel can take the new set of the inputs every 138 cycles. But the trade-off is also the utilization, and here we can see that we need more flip-flop to help us to optimize the data flow of Dct2D. And this is the GitHub link. You can find my source code down there. And this is all my presentation, and thank you for your listening.
So for the next week's lecture, we talk about the data flow that's not complicated to the hierarchy.
Yeah.
That's why
yeah.
Another way is you put the data flow inside the.
Yes.
Another way.
Yes. Yes. Yeah, it's an alternative. You can either put it into. Yeah. Oh, yeah, it's a really good suggestion. Okay.
Also, that's a very. I think I suggest you go back to this follow. That's a very typical, very classical optimization process. Okay, you remember this starts with the pipeline.
Yes.
Okay, don't jump to data flow right away. Because for each task, you have to make sure it's throughput. So in this lab, we start with the pipeline for each function.
sure the pipeline, you eliminate all the bottlenecks for pipeline. Yeah. Remember, there is a bottleneck is the memory port.
Yes.
Yeah. So you have to overcome the things to make sure you have some the best optimize the pipeline first. And then you add the data flow to function. I would suggest really go detailed study. Yeah, it's very good.
Thank you, Professor Wang. Yes, please.
When you apply data flow, the true data flow.
I'm sorry, can you repeat it again?
Is there any problem you encountered when you apply the data flow pipeline?
Oh, actually, I just add you just click the right button and you just click the data flow option. You select that option and you can just compile it and you generate the new design. So no.
So the code itself is in the canonical form of data flow. And there's no need to change the source code. Yes.
No, I didn't change the source code. Yeah, thank you.
So I would say for the whole optimization process, you didn't change the source code except the one. If
Yeah, is that the one?
That's the only place you modify.
Mm.
Yeah. Then you apply only the pipeline.
Yeah, then I just apply the pragma. Yeah.
So can you say on the initial how many cycles? 5,000 cycles?
Yeah, 5,000.
5,000.
Around 5,000. Yeah. Actually, the 5,000 one is a latency, and in the final version we still have 500 latency, but the interval is 138. Yeah.
The interval of the frame rate.
Yeah. Because if the number of these function is called that approach the infinitive, that the throughput is 1 over the interval. Yeah, 1 over interval. So what interval is actually interval matters then. Latency doesn't matter actually. Thank you.这个吗？对。然后这个，然后换页是，
哎，哦，哦，哎，等下，hello, I'm Zhang Heten. My, eh, in this tutorial, we will see a very simple matrix multiplication, which multiply only 3 by 3 matrix, but it took me several working hours to get things work, include cosine and understand the latency, but I still have a lot of things that I don't understand, so I will appreciate that you guys can think what happened there with me together. So this is the baseline implementation in this tutorial. As we can see, there is a for loop corresponding to the row index iteration and call loop corresponding to the column index iteration and product loop, which compute each entry of the resultant matrix. Okay, so let's first turn off all the optimization that performed by default Vitis setting. And we can see all the loop hierarchy are preserved. And I asked myself, what is the difference between blatant and unroll? And I searched on the internet. I see that blatant loop eliminate the loop hierarchy, but it is different from unroll. Blatant eliminate the for loop hierarchy, but it still do the job in pipeline manner. But for unroll, it copy the loop body in several instances, such that those instances can work concurrently. Okay, so let.
Non-related. That's independent.
Yes.
Yeah.
Yes.
So even though you don't flatten, you still can enroll.
Yes.
You flatten, you can enroll.
Yes.
Yeah. So independent. And flatten reduce the latency.
Yes.
Okay, but that don't provide parity.
Yes.
Enroll provide parity.
Oh, yes. Thank you. If I misunderstand something, feel free to tell me. Yeah, thank you. Let's observe the latency of the baseline solution. You can see, I try to compute single iteration latency and total latency. And the red text shows some guess I made. For example, it seems that here we can see in the first cycle of the product loop, we load the matrix A and matrix B data. But recall that we need one cycle to enter a loop and one cycle to leave the loop. So I think perhaps I guess one of the branch operation, one of the branch of code is merged in the first latency. So we have the single cycle compute as shown here. So the product latency of single product loop is 5. And
except for the product loop. For other, for example, call loop and row loop, I can understand and calculate the correct single loop latency and calculate the final latency correctly. Okay. Any question? Oh, yeah. Oh, yeah. Here I want to mention that I guess perhaps sometimes the branch OP code that enter the loop might be merged with other operation, I guess.
So what's the question? So the iteration latency 5 is okay, right? There's a 5 cycle, right?
Yeah.
Yeah, 1 cycle for loading, 2 cycle for multiplication and addition.
Addition
And
and
then right, take another cycle.
okay.
Write the result. So that's why it's 5 cycle.
Okay, then I think this one is branch. Then branch, I guess it check the leaf condition.
This one is French.
And when we enter the loop, we need another branch checking for the loop condition, and it is one of here, but it merged with load OP code. So we have we have 5. Our latency is 5 instead of 6, I guess so. Otherwise, it should be 6. Because if the
loading and the setup of the loop,
yes,
okay, initialization of the loop overlap with the loading, right?
yes, so we have 5 instead of 6. Because some article mentioned we need 1 extra cycle to enter a loop and 1 cycle to leave the loop. But
but here
we merged.
But here you are talking about the loop for product.
Okay.
So there's no entry and exit.
Okay.
Entry and exit come into the upper level.
Okay.
So in here, 5 cycles, you are talking about only the iteration for this product loop.
Okay.
So no entry and exit comes here.
Okay.
They come into upper level, like this one, the current loop. So the product is 15, right?
Yes.
And then you have 1 entry and 1 exit.
Okay.
Yeah, so that's why for column 17. And 17 times 3 becomes 51. The row has an entry and exit.
Okay.
Yeah.
Then we look one more example. We pipeline the innermost loop. So because we apply pipeline here and II interval is 1. So I think the total latency in the innermost loop should be 7. I don't know why it is 6, but if we use 7 to compute the iteration latency in the next level, it is 9 and correct. But I don't know why here is 6.
So current latency is correct.
Maybe. Maybe I don't know.
Why not report in the forum?
Okay.
Try to report it in Chinese GPU.
Okay. Okay, so Professor Lai suggests me to mention the a situation in the tutorial, but I cannot reproduce the same problems. So I explain, I show the material that Professor Lai suggest, and I also shared what I actually encountered. So in tutorial, there is a problem mentioned in the class too. Carry dependency violation, as shown in the table here. That is, we first read a data and perform some work, such as addition, and write it back. If we pipeline it, we will probably read the old data before we write the new data. So the fetched data is out of date. Okay, so this problem is mentioned in the tutorial, but what I actually encountered is A load and B load are violations. So perhaps in this version of ByteDance, it reports only one of problem. Maybe we also encounter the carry dependency violation, but what it reports is A load and B load problem.
So I think that's you are talking about the startup loop, right? In the startup loop.
Oh yes, yes.
So basically, I think that the new version of this is does the data for the data store the product as a temporary register, so product instead of writing to the product.
Oh, better optimization by default. Oh, okay.
You can say that it produced the II equals 2, right?
Yeah, in both cases, it requires I equal to.
So after you add the result, it forward to the next cycle. You can read the result. You can read the result before you write back to the memory.
Yeah.
So the ByteDance tool just do the data forward automatically.
Oh.
So it can solve sometimes solve the carrier dependency problem.
So in the A71, they mentioned there is a carry dependency violation.
Yeah, in that tutorial, but I cannot reproduce the same problem.
So that's why I remember the PDF file is 2022.
Yeah.
So every document has to match the two versions.
I try to find the latest tutorial, but there is no such tutorial.
Yeah, this document is 2024, and the tool you use is 2024.
Right, yes.
So each new revision of the tool they do something different. Doesn't match.
Okay, let's see one more example about latency analysis. So in this example, I encountered, I have the same question. We can see in the lag text, lag part. I don't have question about this part, but problem start from here. I expect the total latency is 13 in the current loop, and in row loop, the single iteration latency should be 15, but it is computed as 14. So maybe perhaps it merged the branch OP code somewhere that I beyond my expectation, I guess. So if you
So either the entry or exit.
So maybe if you guys someday come up with the answer to this question, you can feel free to tell me. I will appreciate. Okay, so what I did is, you can see this detail in my slide. I compare the effect of different directive pipelining, flattening, and unroll in different loop hierarchy, row, column, and product. And we can see the latency from 160 and improve become 10. And interval also improve, shown in here. But the latency reported in the tutorial is 5. That is, I cannot believe it can achieve the latency equal 5 in the tutorial. But what I show you here is my result. And we can see as the we after more improvement, and the resource usage becomes more. Okay, so in the tutorial, it mentioned about another problem that prevent a loop to be flattened. Because if in the tutorial, you mentioned that when a loop access I/O port of a function, then this loop cannot be flattened. But somehow, after I fix all II violation problem, and all loop has been flattened. So this is another problem that I cannot reproduce the same result in the tutorial.
You were saying that if the loop access the I/O, then it cannot be flattened.
According to the tutorial. But in this version of Vitesse, all loop can be flattened.
No, I think what it means if the I/O is a string.
Okay.
Because string need to be in order.
Yes.
Okay. Then once you flatten the order number, it cannot be flattened.
Okay.
Not the general I/O.
Okay.
I mean the I/O here is the string.
Okay. Okay.
So if you use the streaming I/O,
Oh, you mean something like if I unroll everything and everything run concurrently? Oh, I see that warning message.
Then probably cannot. Because you access the I/O using the stream interface.
Okay.
You probably cannot unroll. So once you unroll, you duplicate the other resource. Right?
Oh, yes.
And each one want to access the stream I/O.
Yes.
But the order is determined.
Yes.
Because streaming requires the order access.
Yes. Okay. Thank you.
I think
Okay. So now we look at the part 2 of this tutorial. In part 2 of this tutorial, it suggests to observe the matrix access order and propose a improvement. In this figure is the figure 7-20 from the tutorial. We observe first block here. So the small square shows the index of row and column respectively. And here in A and B, it shows the matrix access pattern. For example, in this red block, matrix A repeatedly read the same row 3 times. Read the same row. And matrix D read the whole, it is accessed 3 times. No, sorry. 3 times. Yes, matrix B read is accessed 3 times in the whole process. And in each row index I whole matrix B is accessed. And for the resultant matrix, it accesses the same element 3 times in a row I block. So if we want to access this data in using FIFO or streaming interface, we need to guarantee they are accessed sequentially. So we need to fetch the data in a local storage. For example, for matrix A, we can have an array that fetch a row, and the fetched data can be repeatedly used for 3 times. But for matrix B, we need to catch the whole matrix and reuse it 3 times. So this is the source code of the proposed improvement, and it used 2 more directives to improve to eliminate the BRAM port bottleneck. For example, reshape the matrix B with dimension 1 means that here we have 3 by 3 matrix B. The first dimension is divided into 3 parts, and each of these 3 parts will be stored in a respective DRAM such that they can be accessed concurrently. And another thing to be mentioned is that in order to achieve this concurrency, the array reshape direction should be perpendicular to the matrix access direction. For example, in array B, array B is the second matrix in the matrix multiplication. So the array B is accessed in the vertical direction, right? So we need to reshape the array according to the first dimension. First dimension means that it partitioned vertically. Because we partition the array vertically, so each element in a single column are stored in an individual DRAM, so they can be accessed concurrently. Okay, so here is a challenge. It took me several days to check my setting if I did anything wrong, but I cannot figure out, so I use a workaround solution to make it work. So CSIM work, but COSIM mismatch. Maybe there's a bug, or the directive shown in the tutorial is invalid. I'm not sure. So this is my workaround solution and my investigation step. First, I try to narrow down the affected scope. I try different combinations of directives and ports, and finally I found whenever we use reshape, not necessarily FIFO, whenever we use reshape on matrix B, I will encounter the COSIM mismatch. So I start to have some guess here. But recall that we apply reshape and FIFO to matrix A2 without any problem.
If you reshape matrix A,
Yeah.
only the matrix.
Yeah. So I'm a software guy, so I try to guess what's the difference. Why we can apply this thing to matrix A, but we encounter a problem to matrix B. So maybe it's related to original data alignment. and therefore its access order. And for matrix A, because the matrix A is read in this direction in row manner, so it follows the data alignment in C language, and therefore it's compiled. Yes.
For this cosine, you are talking about using the string, right? Using the string.
Streaming.
Which level you run?
In fact, first lab, it suggests to use reshape, but I encounter this problem whenever I use reshape to matrix B. So, okay, maybe it is because of the alignment of the matrix. So my guess is, okay, perhaps we just simply transpose matrix B and swap index.
So that's when you prepare the test data, you apply the transpose.
Yes.
You have a host program prepare the data for the array A and array.
I modified the kernel function such that the index is swapped. IKJK.
So I thought you modify how you prepare the array data.
Oh, if with the swapped index, if we want to compute the same result, and we also need to modify the input data. Yes.
Right?
Yeah, you are correct. Yeah, we also need, yeah. So we need to, like Professor Lai mentioned, we need also modify our input data. And okay, now cosine work. Yay. Okay, this is my presentation. Thank you.
Okay. Yeah. Can you go back to the previous slide? Show the data access. So actually, in here, this is a very typical optimization. This is a very good technique. That, in here, we want to apply the string interface. Okay, because the string interface is much more efficient. And data comes in that you reduce the I/O in here. In here, you reduce the I/O access. For each matrix A and B, you don't repeat the access. Right? Okay. Then you also don't fetch the whole array. And matrix multiplication is very, very important in many applications. Okay? It's important. Yeah. So matrix computation is a very common operation in many applications. It's in the scientific computation. It's also useful for graph. Okay, so like page ranking is also matrix multiplication. Yeah, and so how you deal with the big matrix, the dimension like millions of dimensions. That's a course. 我会用到几点？应该要下课了。好 ，maybe 在5分钟。好。Okay. So there's one technique that, let's say that matrix is so big, you simply could not save in the on-chip memory. You have to get access from the I/O. So you want to reduce the number of times to access the matrix from the memory, from the external memory. So you need to cache in the on-chip memory. And in here, how much you cache that, for example, for the result, there are many optimization here. Like the result, you only write out once. Okay, you don't, for original code, you have to write out 3 times. For each matrix element, you have to write 3 times, but you only write once. Okay, and for the matrix A and B, you only read in once, although you access multiple times, but you only read in from memory once. Yeah, and you only cache the necessary element in the, or minimum of the minimum size of a matrix in the on-chip memory. Yeah, and also using the stream interface. Yeah. So the way often in our optimization, when we doing the acceleration, most of the time we deal with the memory access pattern. Okay, so you observe it's a access pattern, then you devise figure out a good caching scheme. Okay, the caching scheme reduce the on-chip memory size, reduce the I/O access. So this is a very good example that apply those techniques. Yeah. In the future, when you run into any accelerations, always think about how this example can be. This is a very general technique. Yeah. Okay. Okay. So we have one more presentation. So maybe we move to next week. But next week we have a lot more presentation. Okay. Maybe we need to find actual hours.